I want to make a claim that will frustrate everyone who has grown up on science fiction, everyone who has been told that humanity is destined for the stars, everyone who finds genuine meaning in the idea of our species spreading across the galaxy. The claim is not that interstellar travel is technically difficult, that everyone already knows. The claim is more specific and more fundamental. The universe has been designed, if that word can be used, with a set of physical laws that make interstellar travel not merely hard, but in several distinct and overlapping senses close to impossible. Not impossible as in the engineering challenges are severe, impossible as in the laws of physics themselves conspire against it. I am going to go through each of those laws in turn because I think the individual obstacles are well known, but the combined picture is not. When you see all the barriers together, the energy barriers and the radiation barriers and the biological barriers and the time barriers and the destination barriers, the honest conclusion is that even a civilization vastly more advanced than ours would face a journey to the nearest stars that would strain any plausible technological solution and would kill its crew unless extraordinary measures were taken. And then I want to draw out the implication that I find most significant, which is what this means for the question of whether other intelligent civilizations in the galaxy have managed to travel between stars if the same physics that constrains us constrains them, and if the nearest habitable planets around other stars are as hostile as the evidence suggests, then the great silence of the universe, the absence of any confirmed contact with other civilizations, may not reflect the absence of intelligence. It may reflect the universe's systematic unwillingness to allow the kind of interstellar spreading that science fiction assumes is natural. Let me start with the most fundamental barrier, which is energy. Moving a massive object from one place to another requires energy. The amount of energy required to accelerate a mass m to velocity v is relativistically E equals m times c squared times the quantity gamma minus 1, where gamma is the Lorentz factor 1 over the square root of 1 minus v squared over c squared. At low velocities, this reduces to 1/2 mv squared, the classical kinetic energy. At velocities approaching c, the energy diverges. Gamma approaches infinity, and the energy required to further accelerate the mass becomes unbounded. Let me give you specific numbers that make the scale of the problem concrete, because the abstract energy formula needs physical anchoring to feel real. The annual energy consumption of human civilization is approximately 6 times 10 to the 20 joules. This is the total energy from all sources: coal, oil, natural gas, nuclear, renewables, everything. It is the energy our species uses in 1 year to run all our transportation, industry, heating, computing, and every other activity. For a crewed interstellar mission, the minimum payload mass must include life support, food and water for the duration of the journey, radiation shielding, propulsion fuel for deceleration at the destination, and the structural mass of the vehicle. A conservative minimum for a crewed spacecraft capable of sustaining a small crew is perhaps 1,000 tons, though most detailed mission designs require much more. Let us use 1,000 tons as a lower bound. To accelerate 1,000 tons to 10% of the speed of light requires approximately 4.5 times 10 to the 21st joules of kinetic energy. This is approximately 10 times the total annual energy consumption of human civilization on Earth. To reach 20% of C requires approximately 4 times more energy. To reach 50% of C requires approximately 7 times 10 to the 22nd joules, approximately 60 times the total annual energy production of humanity. These numbers assume perfect conversion of energy to kinetic energy of the spacecraft with zero waste. In practice, any propulsion system has efficiency less than 1, and the energy requirement increases accordingly. Chemical rockets have specific impulse of approximately 450 seconds, corresponding to exhaust velocities of approximately 4.4 kilometers per second. The escape velocity from the solar system is approximately 42 kilometers per second. To accelerate a spacecraft to even 0.1% of the speed of light using chemical rockets would require a mass ratio larger than the number of atoms in the observable universe. Chemical rockets cannot reach interstellar velocities. The fundamental problem is the Tsiolkovsky rocket equation. For any rocket that carries its own propellant, the mass ratio, the ratio of initial mass to final mass, equals e to the power of delta v divided by exhaust velocity. For exhaust velocity of 4.4 kilometers per second and delta v of 30,000 kilometers per second, 10% of c, the exponent is approximately 6,800. The mass ratio is e to the 6,800, a number with approximately 3,000 digits. This is not an engineering challenge. It is a mathematical impossibility. Nuclear thermal rockets improve the exhaust velocity to approximately 9 kilometers per second, reducing the exponent to approximately 3,300 for 10% of c. Still completely impossible. Nuclear pulse propulsion, in which nuclear bombs are detonated behind the spacecraft, could in principle achieve exhaust velocities of 30 to 10,000 kilometers per second, corresponding to specific impulse of 3,000 to 1 million seconds. At the optimistic end, the mass ratio for 10% of c becomes e to the 3, approximately 20. A mass ratio of 20 means 19 kilograms of fuel for every kilogram of payload. This is aggressive but not impossible for a crewed interstellar probe. But nuclear pulse propulsion has fundamental barriers. The Partial Test Ban Treaty of 1963 prohibits nuclear explosions in space. Repealing or circumventing this treaty would require international agreement that is politically inconceivable in any near future. Building the thousands of nuclear bombs required for an interstellar mission would require enriching sufficient nuclear material to represent a significant fraction of the world's current nuclear arsenal, with the proliferation and security implications that implies. The only propulsion concepts that sidestep the rocket equation are those that draw energy from external sources rather than onboard propellant. Laser sail propulsion, in which a powerful laser on Earth or in the solar system accelerates a lightweight sail, is the most physically credible such concept. The Breakthrough Starshot Initiative proposes accelerating gram-scale probes to 20% of the speed of light using a 100 gigawatt laser. The critical limitation is the mass. The energy required scales with mass, and the laser power required to accelerate a human-scale spacecraft to interstellar velocities would be comparable to the total power output of the Sunday. This is not currently achievable and may never be achievable with any technology we can envision. If this is already changing how you think about humanity's place in the cosmos, the principles I have developed for understanding the fabric of reality address exactly this: what the universe allows and what it does not. Ready to change how you see the world? Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. The second barrier is time. Even if the energy problem is solved, even if a spacecraft can be accelerated to a significant fraction of the speed of light, the journey takes a very long time. Proxima Centauri, the nearest star, is 24 light years away. At 10% of the speed of light, the journey takes 42.4 years. At 20%, 21.2 years. At 50%, 8.5 years. At 90%, 4.7 years. These times are the journey times in the reference frame of the solar system, the frame in which the spacecraft is moving. The crew experiences less time due to relativistic time dilation. At 90% of c, gamma is approximately 2.3, so the crew ages approximately 2 years during the 4.7-year solar system journey. At 99% of c, gamma is approximately 7, so the crew ages approximately 0.7 years during the 4.3-year journey. For distant stars, the relativistic time dilation becomes more significant. A spacecraft traveling at 99% of c to a star 1,000 light-years away would arrive after approximately 1,000 years of solar system time, but the crew would age only about 140 years. A spacecraft at 99.9% of c would have gamma of approximately 22, reducing the crew's aging to about 45 years for a 1,000 light-year journey. At first glance, this seems encouraging. The crew's experienced time is shorter than the journey time in the solar system frame, but several problems remain. The first is that even at 99% of c, a journey to any star more than a few hundred light-years away takes longer than a human lifetime in crew time. The crew would need cryogenic suspension, suspended animation, or multi-generational ships. None of these is currently achievable. Cryogenic suspension of humans for years or decades has not been demonstrated to be biologically feasible. The second is the communication time delay. At any velocity below c, messages to and from the spacecraft take time. A spacecraft at 42 light-years distance has a 42-year round-trip communication delay. The crew cannot consult with Earth in real time. Any emergency must be handled autonomously with onboard resources. The third is the return trip. For a round trip, all the energy expenditure must be repeated in the other direction. The round-trip energy requirement is approximately double the one-way requirement, and the destination provides no infrastructure for refueling or repair. The fourth is deceleration. Accelerating to high velocity is only half the problem. To arrive at the destination at a manageable speed, the spacecraft must decelerate. Deceleration requires the same energy as acceleration. The total mission requires approximately twice the energy of a one-way coasting journey. For a 1,000-ton spacecraft making a round trip to Proxima Centauri at 10% of c, the total energy required, accounting for acceleration and deceleration in both directions, is approximately 4 times 10 to the 22nd joules. This is approximately 30 times the annual energy production of humanity. With any currently conceivable energy technology, this is not achievable. The third barrier is radiation. Interstellar space is not empty. It is permeated by cosmic rays, high-energy charged particles accelerated in supernovae, and other violent astrophysical processes. I described the cosmic ray problem in detail in the Mars video and the Proxima Centauri b video. Let me develop it here specifically for high-velocity interstellar travel, because the problem has a qualitatively different character at high speeds. At the velocities achievable in the inner solar system, cosmic rays arrive from random directions and interact with shielding material. The shielding problem is difficult but manageable with appropriate material thickness and composition. At interstellar velocities, two new effects emerge that change the problem qualitatively. The first is the Lorentz transformation of the cosmic ray spectrum. From the perspective of a spacecraft moving at velocity v, the cosmic rays are boosted to higher energies. A cosmic ray proton with energy E in the solar system frame appears in the spacecraft frame to have energy approximately E times gamma times 1 plus V over C, which for a proton at 10% of C is approximately 1. 0, 0, 5 times the solar system energy, negligible. But at 90% of C, gamma is approximately 2.3, and the boost factor is approximately 4.2. The cosmic rays appear more than 4 times more energetic. At 99.9% of C, gamma is approximately 22, and the boost is approximately 44 times. The cosmic ray flux also increases. More particles per unit time arrive because the spacecraft is moving toward them at high speed. The second and more fundamental problem is the interstellar medium itself. The average density of neutral hydrogen in the galactic plane is approximately 1 atom per cubic centimeter. At 1% of the speed of light, a hydrogen atom impacting the spacecraft front has a kinetic energy of approximately 4.4 MeV, well above the ionization threshold but below the threshold for nuclear reactions. The hydrogen atoms are a source of ionizing radiation but not of high-energy secondary particles. At 10% of C, the hydrogen atom impact energy is approximately 440 MeV, approaching the threshold for pion production in proton-proton collisions, approximately 280 MeV. At this velocity, some fraction of the hydrogen impacts produce pions, which decay into muons and gamma rays. The spacecraft front becomes a source of secondary radiation. At 50% of C, the hydrogen atom impact energy is approximately 2.4 GeV, well above the pion threshold. Nearly every hydrogen atom impact produces multiple pions and a shower of secondary particles. The spacecraft is flying into a continuous beam of hydrogen atoms that it must convert into energetic particle showers. No passive shielding can stop a continuous flux of GeV energy protons and secondary pions. A concrete calculation illustrates the severity. At 50% of C, the flux of hydrogen atoms striking the spacecraft front is approximately 1 atom per square centimeter per second times the Lorentz factor times the flux enhancement from the spacecraft's velocity. The power deposited in the shielding material by these collisions, calculated from the stopping power of GeV protons in aluminum, is approximately a few watts per square meter. For a spacecraft front with an area of 1,000 square meters, this is a few kilowatts of continuous radiation power deposited in a thin layer at the front of the spacecraft. This is not negligible. Over a 5-year transit, it represents the continuous irradiation of the spacecraft's forward face with the energy equivalent of millions of chest X-rays per square centimeter. The shielding required to protect the crew from the boosted cosmic rays and the interstellar hydrogen flux at high velocities is not merely a matter of adding more mass. The third barrier is radiation. At high velocities, approaching the speed of light, the cosmic ray problem becomes dramatically worse. Magnetic shielding, using a superconducting magnet to deflect charged particles around the spacecraft, has been proposed. The minimum magnetic field required to deflect a 1 GeV proton with a 100-meter deflection radius is approximately 0.03 Tesla, which is achievable but requires a superconducting coil system of substantial mass and complexity. The field must enclose the entire crew volume, not just the front face, because the magnetic deflection creates a halo of radiation spiraling around the field lines toward the sides and rear of the spacecraft. The engineering of a practical magnetic shield for an interstellar spacecraft at high velocity is a profound and unresolved problem. At velocities above approximately 10% of C, another factor emerges: the impact of dust grains. Even at low mass, a dust grain moving at 10% of C has an energy comparable to a high explosive round. A microgram dust grain at 10% of C has a kinetic energy of approximately 4.5 megajoules, comparable to the energy of a kilogram of TNT. At these velocities, the impact of interstellar dust becomes a catastrophic threat rather than an erosion problem. The barriers we are examining reveal something profound about the structure of reality. The universe has a specific set of rules, and those rules close certain doors very firmly. Understanding which doors are open and which are closed is one of the 12 principles in my book. Get 12 principles for understanding the fabric of reality at realityprinciples.com. The fourth barrier is biological. Human beings are adapted to the surface conditions of Earth. 1, gravity, a specific atmospheric pressure and composition, a specific temperature range, a specific radiation environment. Space travel removes all of these familiar conditions and replaces them with conditions hostile to human physiology. I described the biological problems in the Mars video in detail. For interstellar travel, the same problems apply but amplified by the much longer duration. Bone and muscle loss in microgravity proceeds at approximately 1 to 2% per month. A 5-year journey to Proxima Centauri at 10% of C would result in catastrophic loss of bone and muscle unless artificial gravity is provided. Artificial gravity through rotation requires a rotating habitat of sufficient radius to produce acceptable Coriolis forces. For a rotation rate of 2 revolutions per minute, a radius of approximately 225 meters is required to simulate one Earth gravity. This adds enormous structural mass and complexity to the spacecraft. The cumulative radiation dose over a 5-year transit at 10% of C in interplanetary space, shielded by the spacecraft structure, would be several sieverts. This exceeds the current NASA career limit and would significantly increase the lifetime cancer risk. The cognitive impairment from galactic cosmic rays, demonstrated in animal studies, would accumulate over the 5-year journey and potentially impair the crew's ability to operate the spacecraft effectively. The psychological challenges of 5 years in a confined space with no possibility of rescue or resupply, communication delay of months, and complete isolation from Earth exceed anything demonstrated in human psychology research. The longest human spaceflight to date is approximately 437 days. 5 years is more than 4 times longer. No behavioral studies have been conducted on groups isolated for this duration, and the extrapolation from shorter mission data is uncertain. For journeys of many decades or centuries, the biological problems are compounded by generational ones. The crew members who depart will not be the ones who arrive. Children born during the journey must be prepared to complete a mission that was begun before they were born, to arrive at a destination they have never seen in a spacecraft that is their entire world. The psychological and ethical dimensions of multi-generational ship design are profound and unresolved. The 5th barrier is the destination. I described Proxima Centauri b in detail in the video about the nearest Earth-like planet being a death trap. The situation is the same for every nearby red dwarf star. Its habitable zone planets are radiation blasted, tidally locked, and stripped of atmospheres by the intense stellar wind and flare activity. The planet around the nearest star is not a welcoming destination. For solar-type stars, which have more hospitable radiation environments, the distances are much larger. The nearest solar-type star with confirmed planets is a matter of ongoing search. Alpha Centauri A and B, the other members of the Alpha Centauri system at 4.37 light-years, are solar-type stars but have not been confirmed to have planets in their habitable zones. The nearest confirmed Earth-like planet in the habitable zone of a solar-type star may be tens or hundreds of light-years away. For every additional factor of 10 in distance, the energy requirement increases by a factor of 100 for the same velocity, the journey time increases by a factor of 10, and the crew's biological problems accumulate proportionally. A journey to a solar-type star at 50 light-years at 10% of C takes 500 years. This is not a mission design. It is a geological timescale. The cumulative effect of all these barriers, the energy barrier, the time barrier, the radiation barrier, the biological barrier, and the destination barrier, is a total obstacle that no current technology comes within orders of magnitude of overcoming. Each barrier alone is sufficient to make interstellar travel with current technology impossible. Together, they create a framework of physical law that makes the interstellar journey extraordinarily resistant to any technological solution. Let me now draw out the Fermi paradox implication. because I think the combined picture of interstellar travel barriers has a specific and important answer to the question of why we see no evidence of other civilizations. The Fermi paradox, as I described in the Aliens video, asks why, given the age of the galaxy and the existence of billions of potentially habitable planets, we see no evidence of any civilization other than our own. The usual answers involve either the rarity of life and intelligence, the self-destruction of civilizations, or the deliberate choice of civilizations not to expand. But there is a fourth answer that I want to develop here, which is the physical impossibility of the kind of galaxy-colonizing expansion that the Fermi paradox assumes must have occurred if intelligence is common. The assumption is that a sufficiently advanced civilization would spread across the galaxy within a few million years at a small fraction of the speed of light. If civilizations are common and the galaxy is 13 billion years old, it should have been colonized long ago. But the barriers I have described are not specific to human technology. They are consequences of the laws of physics that apply to any civilization anywhere in the universe. The Tsiolkovsky rocket equation applies to any rocket-based propulsion in any physical theory based on conservation of momentum. The energy requirements for interstellar travel are set by the kinetic energy formula and the mass of the spacecraft, both of which are consequences of special relativity. The radiation environment of interstellar space is determined by the distribution of supernovae and cosmic ray sources in the galaxy, not by anything specific to Earth. The interstellar medium density is an astronomical fact. The biological fragility of carbon-based life is a consequence of the chemistry of organic molecules. A civilization with vastly superior technology might circumvent some of these barriers. They might develop fusion drives or antimatter drives that achieve specific impulse orders of magnitude better than chemical rockets. They might develop perfect radiation shielding or biological modifications that make their crew radiation resistant. They might find a different propulsion paradigm that does not require carrying onboard propellant. But even the most optimistic technology cannot completely eliminate the energy barrier or the time barrier. The fundamental constraint is the speed of light. Even at sea, a journey across the galaxy takes 100,000 years. No matter how advanced the propulsion, a civilization that wants to colonize the galaxy must be willing to commit to journeys of at least hundreds of years for nearby stars and much longer for the full extent of the galaxy. A civilization willing to make this commitment would need to maintain a stable, organized interstellar program over timescales much longer than any human institution has ever maintained. Human civilizations have existed for a few thousand years. The Roman Empire lasted 500 years. The Catholic Church, one of the most durable human institutions, is 2,000 years old. An interstellar colonization program requires sustained effort over timescales of thousands to millions of years. The barriers to interstellar travel are not just physical, they are also organizational, motivational, and existential. A civilization that survives for millions of years while maintaining a coherent program of interstellar expansion would be extraordinary in ways that go well beyond its propulsion technology. What the universe is telling us through these barriers is something profound about the nature of intelligence and existence in a cosmos governed by specific physical laws. The principles that illuminate this, that help us understand what kind of beings can persist and flourish in such a universe, are in my book. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now address the most important counter-argument to everything I have said, which is the possibility of physics beyond the standard model that would change the energy calculus of interstellar travel. Wormholes, as I described in the Aliens video, are solutions of Einstein's field equations that connect two distant points in space-time through a shortcut. If traversable wormholes exist, a civilization could create a wormhole connecting two stellar systems and travel through it in a time much shorter than a direct journey would require, even at sea. The problem with traversable wormholes is that they require exotic matter with negative energy density. No known form of matter has negative energy density, and quantum field theory imposes constraints on how much negative energy can be generated and maintained. The Ford-Roman constraints show that the negative energy density required for a traversable wormhole must be concentrated over an extremely small region and must be supplemented by large positive energies elsewhere, with a net energy budget that makes a macroscopic wormhole require more energy than is contained in the observable universe. These constraints are derived from the semi-classical approximation to quantum gravity, which is reliable for all macroscopic systems. Whether a complete theory of quantum gravity, string theory, or loop quantum gravity, or something else allows traversable wormholes is unknown. The ER equals EPR conjecture, connecting entanglement and geometry, suggests that wormholes and quantum entanglement are related. But even if quantum gravity allows wormholes, whether they can be made traversable and useful for transportation is a separate and unresolved question. The Alcubierre warp drive metric has the same exotic matter problem. Creating and maintaining the warp bubble requires negative energy density at specific locations in amounts that scale with the size of the bubble. A bubble large enough to contain a spacecraft requires negative energy comparable to the mass energy of Jupiter. The honest assessment is that neither wormholes nor warp drives are physically achievable with any known physics. They require exotic matter that does not exist in the known laws of physics and that may not exist in any quantum gravity extension of those laws. Other proposed solutions include ramjet propulsion, in which the spacecraft scoops up interstellar hydrogen and uses it as fuel in a fusion reactor, avoiding the need to carry propellant. The concept was proposed by Robert Bussard in 1960 and became a staple of science fiction. The problem is that fusion of ordinary hydrogen protons is extraordinarily difficult. It requires temperatures and pressures far above what any plausible magnetic confinement system can maintain on a spacecraft. The interstellar hydrogen must be collected over an enormous cross-sectional area, requiring a magnetic scoop of implausible size, and the drag from the collection process may exceed the thrust from the fusion. Generation ships and cryogenic suspension, while not solving the energy problem, address the time problem by different means. Generation ships require a self-sustaining ecosystem and a stable social structure maintained for centuries. Cryogenic suspension requires a biologically reversible method of reducing metabolism to near zero for decades, a medical technology that does not currently exist. Each of these proposed solutions is either physically impossible, technologically far beyond any achievable capability, or addresses only one of the multiple overlapping barriers without addressing the others. Let me now address what I think is the most important thing to say about interstellar travel being almost impossible, what it means for how we think about our current civilization and its responsibilities. If interstellar travel is as difficult as the physics suggests, if even the most advanced civilizations in the galaxy face barriers that prevent them from colonizing more than a small neighborhood of their home star, then the widespread assumption that any technological problem on Earth can be escaped by moving to another planet or another star system is false. We cannot move to Mars to escape a degraded Earth. Mars is nearly as hostile as interstellar space, and the energy required to maintain a substantial human population there indefinitely is comparable to running a small industrial civilization on Earth. We cannot move to another star system. The physics is completely prohibitive. The Earth is not a launch pad. It is not a prototype. It is the specific, irreplaceable world that our biology and our civilization have been shaped by over billions of years, and it may be the only such world accessible to us on any time scale that matters for our civilization. The universe has been arranged with physical laws that make the stars inaccessible on the timescales of human civilizations and nearly inaccessible even on the timescales of geological epochs. The barriers are not challenges to be overcome with sufficient ingenuity. They are features of the laws of nature that no conceivable technology can fully circumvent. This is not a counsel of despair. Interstellar travel may still be achieved over very long timescales with propulsion systems we cannot currently envision, using resources of energy that dwarf anything we currently command. Slow ships carrying hibernating crews might make one-way journeys to nearby stars in centuries. The first steps in interstellar exploration might be sending robotic probes like the Breakthrough Starshot concept, which uses the existing physics of laser-accelerated sails to send gram-scale instruments to Proxima Centauri in 20 years. But the comfortable assumption that the universe is a network of accessible worlds waiting to be explored and settled by humanity on the timescales of generations rather than geological epochs is contradicted by the physics. The universe is mostly inaccessible, the barriers are real, and the Earth, imperfect and fragile and temporary though it may be, is the extraordinary accident of conditions that makes our existence possible. The universe is telling us something important. Our place in it is both more constrained and more precious than we usually acknowledge. That insight about the relationship between the laws of physics and the meaning of existence is one of the 12 principles that I believe most fundamentally change how you see the world. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. What barrier to interstellar travel do you find most profound and why? Tell me in the comments. If this changed how you think about the possibility of interstellar travel and humanity's long-term future, if the combined picture of energy barriers and radiation barriers and biological barriers and destination barriers looks more severe than any single obstacle alone, tell me in the comments. Tell me whether the Fermi paradox implication, that the same physics constrains every civilization in the galaxy, changes how you think about the Great Silence. Tell me whether you find the physical barriers to interstellar travel more or less daunting than the organizational barriers, the challenge of maintaining a coherent program across thousands of years. And subscribe if you want to keep going into the places where the laws of physics set limits that determine not just what we can build, but who we are in the cosmos.